Okay, let's unpack this. We're opening up the engine room of computer science today.
Hmm.
We're looking at a simple, truly foundational concept that makes modern computing possible. Iteration.
Or as we all call them, loops.
Exactly, loops. Our mission in this deep dive is to shortcut you past the really dense technical manuals.
Right.
We want to give you the actionable insights on how computers actually handle repetition. We've gone through sources detailing the precise mechanics of C++ loops, and we're really zeroing in on the crucial nuances.
The why for this is, I think, so immediate.
Yeah.
If you just connect this to the bigger picture, our lives are just defined by loops. I mean, think about your day.
Oh, yeah. Wake up, commute, eat, sleep, repeat.
Exactly. That's an iteration. But, what happens to us when we do that? We get tired, we get distracted, we make mistakes.
We forget our keys.
You forget your keys, you miss a detail at work. And that is the core contrast we're digging into here.
Right. Humans are we're bad at repetitive tasks.
Yeah.
We slow down, we make errors, we get bored.
But computers excel at it. They don't have those failings.
They can execute millions, billions of repetitions without a single error and at a speed you can't even imagine. This is the power we're trying to harness.
It is.
But before we get to the big structures, the loops themselves, we have to start small with the micromechanics of just counting.
That's right. Because loops are fundamentally about counting, right? From a start point to an end point, we are constantly adding or subtracting one.
All the time.
And because it happens so often, C++ gives us these special shortcuts, the increment and decrement operators, the plus plus and minus minus.
And here's where it gets really interesting and, well, where a lot of new programmers get tripped up. There are two flavors, and the difference is all about timing.
It is.
So if I write I plus A, that's the post increment. What does that actually mean in the moment that line of code runs?
With the post version, the variable's value is used first
Used first.
in whatever operation is happening. And then after that's all done, the variable gets increased by 1. It's like, use me now, change me later.
Okay, so conversely, if I write plus I, that's the pre-increment. The change happens immediately.
Yes, the change happens first. The value of the variable is increased by 1, and that new updated value is used right away in the current operation. It's change me now, then use the new me.
This distinction matters so much. I remember thinking I plus and plus I were basically the same in a simple for loop header. I mean, they both get you to 10, right? Why does it really matter?
That is a fantastic question because in a simple standalone statement, you're right. Modern compilers are so smart, they often generate the exact same machine code for both.
So the performance difference is 0.
Usually negligible for a basic integer. Where it truly matters is, well, twofold. First, when you use that increment inside a more complex expression.
Like inside a function call or something.
Exactly. The side effect of when that value changes can lead to some really tricky bugs.
And what's the second area where we have to pay attention?
Performance. It becomes critical when you're dealing with more complex data types, specifically something called an iterator. An iterator is often a class object, and that post-increment, the I plus A, actually forces the system to make a temporary copy of the original value before it increments.
Because it needs to return that old value.
Precisely. The pre-increment plus I avoids that copy entirely. So in those cases, using pre-increment is universally recommended. It's just better practice.
That shifts the focus completely. It's not just counting, it's efficient counting. Okay, we've got the micromechanics. Now let's scale up to the loop itself. Formally, iteration starts at a point, runs some code, and then loops back to repeat until a condition is met.
And what's so powerful is the ratio. You write maybe 3 lines of code, and the computer can execute that block thousands of times. But safety is paramount.
Yes.
The single most important rule is that a loop must have an exit point.
Otherwise, you hit the trap. I remember my first time doing this. Just pure panic. You create the infamous infinite loop.
Exactly. It happens when you forget the update, or if you write a condition that's just always true, like while 10 is greater than 5.
And it never stops being true.
Right. The program just runs forever, eating up system resources until it crashes or you kill it manually. It's a rite of passage for every programmer.
A necessary warning, for sure. You need a way out. Okay, let's get into the 4 distinct types C++ gives us. Knowing the right tool for the job is key. We've got for, range-based for, while, and do while.
The standard for loop is the workhorse.
The classic.
It's designed for when you generally know or can calculate how many times you need to run. It has that clean structure, initialization, condition, and updation, all in one line.
And it's surprisingly flexible, right? The sources point out that all three of those expressions are technically optional.
They are. You can put the initialization outside, you can handle the update inside the loop body, you can even cram multiple statements into the initialization or update parts using commas.
Which you can do, but maybe shouldn't for readability's sake.
It's powerful, but can get obscure fast.
Okay, now let's pivot to the range-based for loop. This feels like such a modern, clean alternative.
Oh, it's fantastic.
Instead of messing with indexes and worrying about off-by-one errors, it just executes over a sequence.
You use it with containers like an array or a vector. The syntax is so readable.
It's just for type variable dot container.
Exactly. The type variable is your range declaration, and the container is the range expression. It handles the start, the end, the stepping, everything for you. It eliminates a whole class of common bugs.
So clean. Okay, moving on. What about the while loop? When is this the better choice?
You grab the while loop when you are not sure how many times you need to iterate.
It could be 0 times or more.
Right. If the condition is false from the get-go, it never runs. The analogy is perfect. While you're not tired, keep running. The body only executes as long as the condition stays true.
Like reading from a file. You don't know how many lines are in it?
Perfect example. You just say, while there's still data to read, keep reading.
So that 0 or more is its signature, which brings us to its cousin, the do-while loop.
Right.
This one guarantees the code runs at least once.
Yes. Because the condition check happens at the end after the initial execution. You do the code block first, then you check the while to see if you should go again.
Which is so common for user input, right?
Extremely common. You have to ask for input at least once. Please enter a number. Then you check, while the input is invalid, ask again. The do-while is tailor-made for that.
So we have the structures. Now, what if we're inside one of these loops and something happens? We need an emergency exit.
That's where your flow control keywords come in. Break and continue.
Okay, so break is the big red button.
It is the eject button. It means exit this loop immediately, ignore everything else in the loop body, and jump to the code right after the loop.
But if you're searching a huge list for one item the second you find it,
you break. There's no reason to check the other million items. You save a ton of processing time.
Makes sense. And continue.
Continue is more of a skip button. It says, I'm done with this current iteration, skip the rest of the code in the body, and just start the next iteration immediately.
Oh, interesting. Like for data cleansing.
A perfect use case. You're processing a data set, you find a corrupted record. You don't want to process it, you just want to move on. So you continue and jump right to the next piece of data.
Both are critical for control. Now we get to where the real complexity kicks in composition. Loops don't exist in a vacuum. You can put math, functions, conditionals, anything inside a loop.
And the most powerful composition tool is the nested loop.
Right. A loop inside another loop.
This is where advanced algorithms live. The outer loop repeats everything inside it, which includes running the entire inner loop from start to finish.
I remember when this clicked for me. If the outer loop runs 100 times and the inner loop runs 100 times, you're not doing 200 operations.
You are doing 10,000 operations.
It scales exponentially.
Exactly. This is the crucial insight. 2 nested loops means your complexity is often n squared. 3 loops, n cubed. You need them for many problems, but you have to understand that cost.
The sources gave that great example of printing a triangle shape with asterisks.
A classic. You need 1 loop for the rows, that's your outer loop, and a nested loop for the columns to print the right number of symbols on each row.
It's all about moving from one instance to many. Which brings us to the application. Why does all this mechanical detail matter to you, the person trying to solve a problem?
Because loops are the backbone of automation at scale. Anytime you hear about batch processing or data analysis, loops are doing the heavy lifting.
Let's start with something simple, like math calculations.
Sure. You can write a function to find the area of one triangle, but a loop lets you run that same function on thousands of triangles in a 3D model.
And what about data analysis, like conversions?
A great one. Imagine you have a data set full of timestamps, but they're all just raw seconds. You need a loop to go through each one and use division and the module operator to break it down into hours, minutes, and seconds.
Or calculating body mass index for a whole list of patients.
Or even something clever, like counting the even digits in one big number. You loop, using the module operator to check the last digit, then dividing by 10 to drop it, and repeat.
And finally, we have to mention competitive programming.
Oh, absolutely.
Platforms like Codis, with problems like FizzBuzz or stuck in a time loop. They almost all require loops.
Because they don't give you one input, they give you 100. You have to write one solution that you wrap in a loop to handle all the test cases. It forces you to think about efficiency and scale.
That was a deep dive for sure. So just to recap the key takeaways for you, we looked at the efficiency and timing of increment operator.
The absolute necessity of having an exit point for your loop.
Right, to avoid that infinite mistake.
Yeah.
And the four main structures for fixed counts, range-based for collections.
The while loop for 0 or more iterations, and the do while for a guaranteed once execution.
We also talked about the control you get with break and continue.
And I think the core insight is that this ability to automate repetition without error is the fundamental strength of a computer. Loops are your first and most important tool for harnessing that power, especially when you start nesting them to solve complex problems.
So here's a final thought for you to mull over. We talked about all these complex applications, from calculating medical data for hundreds of patients to solving these intense competitive programming challenges. Considering all that, how does that professional realization that pre-increment plus plus I is often more efficient for complex types fundamentally change your default habit? Do you now commit to always using plus plus I, unless you have an undeniable reason to use the less efficient I plus plus I just for that moment when you need the original value? Think about the power of defaulting to the faster tool. We'll see you next time on The Deep Dive.